Yes, hi everyone, and welcome to this week's 1W-Minds seminar. Today's speaker is Lenaïc Chizat. He obtained his PhD. He did his PhD at Université Paris Dauphine, and he got his PhD in 2017. Since then, he has done postdocs at École Supérieure and another university in Paris. My handwriting is hurting me, but now he is at EPFL and he has been there since 2021. His research concerns, among other things, theory of deep learning, continuous optimization, and also optimal transport, which will play a huge role today. The title of the talk is Two Advances on Sinkhorn's Algorithm. The floor is yours.
Thank you for the introduction, Axel, and hello, everyone. So today I want to talk about two recent results that we obtained last year regarding Sinkhorn's algorithm, which is a method to solve computational optimal transport problems. So in this talk, it will be divided in three parts. First, I will introduce optimal transport, its entropic regularization, and also Sinkhorn's algorithm, which is the standard algorithm to tackle these problems in large-scale settings. And then there will be two parts, one for each of these advances, like of these results. The first one is about tighter convergence rates under some assumptions for Sinkhorn's algorithm. And the third part will be about the annealed Sinkhorn algorithm, which is also known as the epsilon scaling technique, for which I will provide some theoretical analysis. So let me start with the introduction. As I was saying before, do not hesitate to interrupt me if there is some object which is not clear. The goal, this talk should be accessible to a large audience, so I don't want to go too fast. So first, let me introduce the optimal transport problem, which is the one we want to solve numerically in this talk. And in a general setting, is defined as follows. You have two probability measures, mu and nu, which live in some measurable spaces x and y. We typically will make much more assumptions when we want to prove some results, but at a high level of generality, this is what you need. And a cost function c on the product space xy with values in R, which gives the amount of effort which is needed to move one unit of mass from a point x in the first space to a point y in the second space. And what you want is to transport the whole distribution mu to the distribution nu in the most efficient way. And the mathematical formulation, which is due to Kantorovich, is the following. You minimize this optimization problem where the variable is pi, this object here, which is a transport plan. So pi lives in the set capital pi of transport plans, which is defined below here. So transport plans, these are probability distributions on the product space xy, such that the marginal on x is equal to mu, and the marginal on y is equal to nu. And these transport plans, they really describe how you will send the mass from one point in x to a point in y, how much mass will be exchanged between these 2 points. This is the measure of dx dy here. So on this constraint set, the objective to minimize is just linear in pi. This is the integral of the transport cost against the transport plan. And this measures the total amount of effort that you used in your transport. So this problem has many applications. I will not talk about applications in this talk. So I hope it will not be too abstract, but I can quickly mention a few of them. Essentially, it's whenever you need to deal with point clouds or probability distributions in applications, solving optimal transport problems will naturally come up. And so this is why we have countless applications in statistics and machine learning in general. A few of them I've mentioned in the bottom of this slide. Okay, so that's I would say, the main problem that we want to tackle today. But typically, practitioners often solve a slightly different problem because it is slightly easier, which is the entropic regularization of optimal transport, which I will call EOT. So this is exactly the same problem, except that we have added a penalization term to the objective function, which is the Kullback-Leibler divergence between this unknown transport plan pi. And here the reference measure which I've taken is the product measure mu times nu This does not play an important role in this talk. I just choose this reference measure here so that the problem is well posed regardless whether pi has a density or not. But what you want is to penalize the entropy of the transport plan. And here, this penalization will make the problem strictly convex, which is not the case for the original optimal transport problem. And so you'll get better stability properties. The value of the minimum, which I will always write EOT of beta, will be more stable. You'll get more stability also of the minimizers of the problem, and so on. So this is a problem which is also interesting in its own right. It's equivalent to the so-called Schrödinger bridge problem, which is a classical problem in stochastic calculus. And you have this hyperparameter 1 over beta, beta, which is the inverse temperature, which determines somehow the approximation and regularization trade-off that you put into this problem. So the smaller beta, the stronger the regularization, and the higher beta, the smaller the regularization. So when beta goes to plus infinity, you converge to the optimal transport cost. So you get a better approximation property if you want to approximate the optimal transport problem, but typically you will make the problem less strictly convex and it will be harder to solve. So here I've plotted the results of the entropic optimal transport optimal plans for the transport of mixtures of Dirac in 2 dimensions. So you have mu, which is a mixture of 5 red weighted Dirac masses, and nu, some weighted Dirac masses in blue. And when beta is very small, you have a strong entropic penalization on the transport plan, which will force diffuse transports. So the graph of the matching, so here each link represents the amount of mass that is sent between two of the Dirac masses with the width proportional to the mass. And so as when beta is small, you tend to send all the mass everywhere. And as beta increases, you tend to send the mass, like the optimal solution will tend to send mass to fewer atoms. And in the end here, this is very close to the optimal transport plan between these two measures. So do not, again, hesitate to interrupt me. Here, this was the optimal transport problem and the entropic optimal transport problem. And I also want to talk about the discrete case, which I will use often in this talk. So when you have the setting where mu and nu are probability distributions, which are just finite discrete measures, so Dirac masses located at point xy, yi, and with weights mu I, mu j, then you can have a finite dimensional representation of the problem, which is given on the right column here. So you have the marginals will now represented by probability vectors. So here I'm abusing notations. I'm using the same letter mu for the probability vector and for the measure. I think that will make the talk slightly easier to follow if I don't switch the notations between the discrete and continuous case. So here delta is the simplex of dimension n when there's this small index n. So probability vectors. And then the only information that you would need from the cost function will be condensed in this matrix C of size m by n, which contains the pairwise cost between all the points x, y, yj. So this is how you will represent your problem. You have this probability vector representing mu, the probability vector representing nu, and the cost matrix, which is of size m by n. And then the discrete optimal transport problem is a finite dimensional convex optimization problem. So here I also wrote the entropic case with this additional penalization. So the transport cost now is just the Frobenius inner product between two matrices, the cost matrix and the transport plan matrix pi, which lives in this set of transport plans, which in this discrete setting will be matrices with positive entries, such that the sum over the rows equal gives the probability vector representing mu, and the sum over the columns gives nu. So these are these kind of solutions that we are looking for, which we will call still pi. So when beta is plus infinity, which means the case where we have no regularization, the standard optimal transport problem, This is a finite dimensional linear program, a linear objective function over a polytope that you want to minimize. And it has a specific structure. So you get very efficient algorithm. In particular, you can solve it, for instance, with the network simplex algorithm, and you'll get a complexity n plus m times nm, essentially a cubic in the size of the vectors that you want to transport. But in this talk, we will focus on algorithms which have a complexity which is rather quadratic. So the product mn, which would be what we would care about where we are in very large scale settings. So we will trade off accuracy. We won't get exact solutions, but we will get better dependency in the size of the problem. And we will be interested in solving both the entropic case and the unregularized case. So you cannot really hope to do better than this complexity because that's the time it takes just to read, let's say, the cost matrix, which is of size m by n. So in general, this is the best you can hope. Okay, and the last introductory slide will be the introduction of the Sinkhorn algorithm. It's a very old algorithm, more than a century old. So I will introduce it in the discrete setting to fix ideas, although it also perfectly makes sense in the continuous setting. And this algorithm relies on the structure of the minimizer of the entropic optimal transport problem to solve the entropic optimal transport problem. Okay, so Sinkhorn is really solving the case where beta is not equal to plus infinity. So what do we know about the minimizers of this problem? Well, you can define this matrix K ij, which is the Gibbs, it's the Gibbs matrix of the cost function, exponential of minus beta c ij, where this is the entry-wise exponential. So if you had, let's say, a square distance cost, this would be like a Gaussian convolution matrix. So once you define this object and you write down the KKT condition for the entropic optimal transport problem, you see that the solutions must have the following form. It will be this matrix K that you scale on the left and on the right by some diagonal matrices with on the diagonal some vectors A and B, which are unknown, and that's what the algorithm needs to find. These these vectors are positive vectors, and they're related to the Lagrange multiplier associated to the marginal constraints of the discrete optimal transport problem. And an interesting fact as well that you get by writing this optimality condition is that as soon as you have found a transport plan which is of this form, you know that it will be optimal for the entropic optimal transport problem. Okay, so that's a property that is also useful. Whenever you have a matrix of this form, it is optimal for the entropic optimal transport problem between its marginals, in a sense. So Sinkhorn's algorithm exploits this structure and will try to find the two vectors A and B recursively by trying to find a matrix of this form with the correct marginals mu and nu. So you'll start from some arbitrary vectors, positive vectors, let's say 1, vectors of ones. And first you will update A so that the first marginal of this transport plan, of this matrix corresponds to mu. And when you do the computation, you see that you need to set A to have this form. So this is, you need to do a matrix vector multiplication and then an entry-wise division with this probability vector mu. And once you have set A of this form, your transport plan, will satisfy the first marginal constraint. And so then you will try to change B so that the second marginal constraint is satisfied. This gives this formula. But of course, as doing so, this will change the first marginal. And so you need to iterate these two operations and hope that it converges to a solution. And this is true. So that's a theorem of Sinkhorn, which says that if you look at the primal iterates, which are given by this formula, they will converge to the unique solution of the entropic optimal transport problem as the number of iterations goes to plus infinity. So this algorithm is the standard algorithm used to solve entropic optimal transport. There are other algorithms, but perhaps the reasons of its wide application is that there is no hyperparameter to choose. You see here, it's really, there's no choice of learning rate, let's say. It works great on GPU. So there are other algorithms that have this property, but here notice that you just need to do some matrix vector multiplications and pointwise divisions of vectors. And in practice, you often observe very good performance. There are many optimization interpretation of this algorithm, so you can interpret it as alternating Kullback-Leibler projection on the transport plan set. You can also see it as a dual alternating maximization in the alternating maximization on the dual. And there are also several mirror descent interpretation of this algorithm. The use of these interpretations is mostly theoretical. It gives us tools to study this algorithm. Okay, so this is the algorithm that we will study in this talk. Do not hesitate to interrupt me if there is a question about the settings. So far, I was just introducing our context. So now let us talk about the convergence rates that we can get for this algorithm. So typically, the convergence guarantees that exist can be grouped in two categories. On one hand, you have the exponential convergence guarantees with bad constants. And on the other hand, you'll have the polynomial convergence, but with good constants. So let's start with the first one, which are known since the 80s, which tell us that if you define a certain metric over the space of positive vectors, so this is the Hilbert projective pseudometric, which is defined here. You can think of it as the L infinity distance between the logarithm of the positive vectors, although you want also to quotient for some by multiplication by a positive scalar. So that's exactly this metric, the Hilbert metric. And you can show that in this metric, these vectors, so here I just wrote the result for AT, but you'll get the same for BT, they will converge exponentially to optimal vectors. So this is the rate that you get. But unfortunately, the exponential, the contraction is very close to 1, the contraction constant. It differs from 1 by exponential of minus beta times the L infinity norm of the cost. So when beta is large, which means when we get closer to optimal transport, this contraction constant goes very, very close to 1, and essentially you will not observe this convergence, exponential convergence in your numerical experiment. So the proof of this result relies on a result by Birkhoff, which states that when you have a positive vector and you apply multiplication by a positive linear map, which is the case of this matrix K, then you'll get contraction for this Hilbert metric, which is related to the fact that you will average your vectors and that will have a contracting effect. And then this operation is something that we have in Sinkhorn algorithm. We have also entry-wise divisions of vectors, but these ones will be isometries for the Hilbert metric. And since in Sinkhorn's algorithm, you just have matrix vector multiplications of this form and then entry-wise division of this form, you iterate contractions and isometries for this metric. In the end, you'll get a contraction. So that's the first family of convergence guarantees that we get. And so here I'm presenting everything for the bounded cost case. There have been some extensions to unbounded costs, but the story is analogous. And now you have the other kind of results, which are polynomial convergence rates with good constants. So here, one typical way we measure the optimality is they are looking at the dual suboptimality gap. So that would be a positive quantity, which measures how far we are from optimality. At iteration t, I will call it delta t. And you'll get convergence, which is, so here the result I'm presenting is by Tureshensky and co-authors in a paper from 2018, but you can find rates which are polynomial in T coming back to the 2000s. And here you get a 1/T convergence rate as a function of the step size. And so this is much slower than the exponential convergence rate, but you have good robust constant. The dependency in beta is only linear. Okay. So here the proof technique, and I will be very vague. It relies a lot on the algebraic structure of the entropic optimal transport problem. But what you want to show is a sufficient increase property at each iteration. So you want to lower bound the decrease of the dual suboptimality gap by some quantity, which will help you then close, like once you have such an inequality, you can conclude by standard optimization arguments if you're familiar with Poiliak-Lozajevich or Lozajevich inequality, you can think of it as a Lozajevich inequality with exponent 1, in the sense that here, this is analogous to the norm of the gradient. That's what you would get if you do one step of gradient descent in some problems, you'll get the norm of the gradient here. And here, this is the squared of the suboptimality. And if this exponent is 1 here instead of 2, you would get exponential convergence. But here, when you look at the problem, you cannot improve. What you get is this square in the exponent, hence the slow polynomial rate. Okay, so all these rates, what we observe in practice? Sometimes yes, but they do not always capture what we observe. So here I want to show you some numerical experiments where we transport Gaussian distributions, which are truncated to a square on 2 dimensions and discretized on a grid with a quadratic cost. And when we plot, so here this is a semi-log plot of the convergence as a function of number of iterations, we see straight lines. So this shows exponential convergence. So it seems that we are in the kind of the first convergence guarantees that we were seeing. However, when we look at how, so here for various colors, these are various choices of beta, of the regularization parameter, with beta increasing when we go from blue to purple. So the problem becomes harder and harder and the convergence slower. But do we observe these exponentially bad convergence contraction rates? Not at all. So if I plot the contraction, so 1 minus the contraction coefficient, so how much our contraction differs from 1 as a function of 1 over beta, we'll see exactly a linear line, okay? So it seems that instead of having exponential dependency in minus beta, we have a linear dependency in 1 over beta. And in fact, for the case of Gaussian marginals, this is something we can prove. So we did the computation in our paper with Alex and Thomas. So when we transport one-dimensional Gaussians, so here we just looked at the simplest case, one-dimensional Gaussians with different variances, and a cost minus xy, which is exactly equivalent to the quadratic, the square distance cost. Then the asymptotic contraction ratio is 1 minus 4 over beta sigma modulo some higher order term in 1 over beta. So we really get something linear in 1 over beta as we observe here. So now the question is, this is not at all covered by the story that we had previously, these two families of convergence rates. So what are the settings where we can expect to have this kind of exponential contraction with good and robust constants? So that's the problem we have explored with our paper with Alex Delalande and Thomas Vaskevicius. And we have this kind of both worlds results. Best of both world scenarios, under the assumption that we have some continuous distributions. So these are results that do not apply to fully discrete problems. But let's see what the assumptions that we need. So we need to assume that we are transporting of density, measures which are supported on a compact subset of RD. So here I'm presenting the first result where we, which is closest to the previous numerical experiments. If you transport with the quadratic cost and you assume that one of the distributions has a log concave density, and here I insist on the fact that we have only assumption on one of the two marginals, the other marginal can be anything, then you will get a contraction ratio which is linear in 1 over beta, at least asymptotically when beta goes to plus infinity. And this is tight, because that matches the exact rate that we have derived for Gaussians in the previous case. So the setting we consider does not exactly cover Gaussians because we need some compactness, but we can expect that this result is tight because of the Gaussian example. So this is a quite restricted setting because we need to assume log concave densities and the quadratic costs. But in fact, we can prove a much more general result with slightly worse contraction constants in beta to the -2, but which is still polynomial rather than exponential in beta. So here the assumption is just that we need smooth cost on a compact set, and one of the two measures must have a density which is bounded away from 0 and bounded away from plus infinity. Okay. So under these assumptions, we still get this robust contraction constant for the exponential convergence. And we also can prove that asymptotically, so for starting from some large time, the contraction constant will also improve to beta minus 1. Although this time T0, starting from which it will be true, can be large in high dimension. While here, the theta, so in the paper, we have all the explicit constants, and this theta does not depend badly on anything. Everything is polynomial here. Okay, so here, these are the main statements that we have in this paper. We have some refined statements under other assumptions, but here, these two statements, they tell the main story, I would say. And I can give a very high-level gist of the proof of how we can get such results. So,
sorry,
yeah,
can I ask
yeah,
a question?
of course.
Yeah, so maybe a basic question here. When you say continuous setting here, so the density is one of them is continuous. Is that what you're saying?
Yeah.
Mu. So how does it work here? The algorithm here, the Sinkhorn here, it seems like at least you told us how it works for when they're discrete measures. How does it work with continuous? Does the algorithm change?
Yeah, so that's a good question. The algorithm, so I mean, it will not be an implementable algorithm. What we are studying is these iterations, like Sinkhorn iterations, which you can perfectly make sense of in a continuous setting for
Okay.
arbitrary measures. But then,
Okay.
of course, these operations you cannot implement on a computer when it's infinite dimensional. So essentially, we are studying a setting which cannot be implemented exactly, but which captures better the practical behavior you get, even in the discrete setting, as long as there is some continuous problem underlying. I mean, if you're solving problems which are discrete, but which are the discretization
Yes,
of
And then what
some
happens?
continuous problem, then you
Yeah.
will observe rates which are as the ones that I'm showing. So for instance, in these
Okay.
Gaussian
Okay.
experiments, we've
Yeah.
implemented it on a grid, on a discrete grid. So it's really
Right.
the empirical observation, and the rates that you observe will be captured by this analysis rather than the discrete one. And in fact, in the new version of the paper, which will be on archive soon, we have some guarantees for discrete problems just by adding some discretization error terms.
So provided that these were actually samples drawn from a concave density kind of thing.
Either samples or discretization on a grid, essentially, exactly. What you want is to be able to have a good enough approximation of the smooth C transforms, which are these matrix vector products.
Okay, thank you.
And what you will get in practice is these rates, but until some threshold where the discretization error will start to be visible.
Okay, thanks.
But that's a good question, important question. Yeah. So I will quickly mention how at a very high level, how the proof works by just giving the two main steps. So I will call psi-t the dual iterates. So these are obtained from these vectors B that you have during your iterates of Sinkhorn by taking their logarithm. Okay. And our starting point is an improvement of this sufficient decay inequality, which I rewrote. So that's the one I've shown previously due to Dvuryshinsky and co-authors, which I rewrote in a different form here, which is exactly equivalent. So I remind you that what we would like to get exponential convergence is to remove the square root essentially here. If we remove the square root, then we can get exponential convergence. But of course, in general, we cannot remove the square root. What we can do in general is by analyzing in a slightly finer way the structure of the entropy coefficient transport problem, is replacing this inequality by the one here, which has two terms. One of them is exactly like we want. So we have the sufficient decay without the square root. So if we had only this, we would get our exponential convergence rates. But then there's another term which still has the square root, but where we have a multiplication by here this is the distance of the dual iterates to the dual solution measured in L2 distance. So this is the variance under nu. Okay. So if this quantity also goes to 0 as we progress through the algorithm, then we'll get some improvement over our square root, okay? And so now we want to, what we want to get is some improvement over this quantity. To show that this quantity will go to 0 at a certain rate along the algorithm progresses. And since this is the distance to the solution in the dual iterates, what we want is some strong concavity of the dual problem. And for this, we exploit some ideas that have been proposed by Alex, our co-author, in a previous paper, that give strong concavity estimates of the dual objective, which are polynomial in beta rather than exponential. So the exponential ones are easy to get, but the polynomial ones are very subtle, and they follow from Prekopa-Leindler inequality, some results in functional analysis. And using these results, we can upper bound this distance via some terms, which will depend in some ways on beta. And essentially, once we get this inequality, so which comes from these inequalities, which follow in part from the structure of Sinkhorn's algorithm and on the strong concavity of the dual, then we can close the argument and show the contraction at an exponential rate. So this is our proof technique. There is a recent extension of our results, like this exponential convergence with robust constant in the non-compact case by Carini and co-authors, which has appeared a few weeks ago. And they managed to remove the boundedness assumption on the cost via a different proof technique. So I will not go deeper in the proof of this result because it quickly gets quite technical and relies on specific algebraic properties of entropic optimal transports. But these are the two main steps that we have in the proof.
Sorry, another question. This
Yeah.
is new to me. So, Bernstein's and Höfting, why is the concentration? What is the randomness here?
So there's no randomness, but there are some integrals against some measures, and we can interpret them as expectations. So here,
okay.
it's more, these are more keywords to explain at a high level the kind of steps we have done rather than exactly some stochastic. There's no empirical process supremum to bound at all. It's more philosophically. Bernstein inequality, we use the second order, like the moment, second order moment information of the distributions to get to tighten certain inequalities, which Höfting does not see. And that's philosophy at a high level. That's how we got the intuition of doing what we did. Although it's not exactly what goes in the proof. Yeah. It's more for the intuition.
Thank you.
Okay, so that's all for the first part. We can I can take also questions later about it. So the second part is quite independent from the first one because we will ask ourselves a very different question. Rather than studying Sinkhorn algorithm as an algorithm to solve entropic optimal transport, we'll study it as an algorithm to solve optimal transport without regularization. And the typical way Sinkhorn's algorithm is used in practice, so here I will present it again in the discrete setting. Everything in this second part is purely discrete. The usual way Sinkhorn's algorithm is used in practice is not with a constant inverse temperature beta, but with a varying one. And typically, we will use a regularization that decreases along the iteration. So this corresponds to beta increasing along the iteration. In this talk, I will call this annealing schedule. And so instead of considering a fixed Gibbs kernel here, K, you'll have a time-dependent temperature. And so the kernel K will depend on the iteration. And you just take the same algorithm as Sinkhorn's, except that you will use your current kernel at iteration K, which is KT. So that's a simple modification of Sinkhorn algorithm. And that's really the main way Sinkhorn is used in most large-scale applications. So if you look at optimal transport packages like in JAX, in Python or other languages, these computational packages, they propose to use Sinkhorn with an annealing schedule beta t, which is exponential in time. So usually they parameterize it with 1 over beta, and this will decay exponentially to 0 along the iteration, except that they typically cap it to some maximum value of beta. But for the purpose of this talk, we will not consider a maximum value of beta, because for the analysis, we want to understand if this algorithm works. So we want to understand if you can solve unregularized optimal transport via this technique. Okay. So the main question is, if you consider the primal iterate corresponding to this algorithm, will it converge to some optimal transport plan without regularization? So as the iteration count goes to plus infinity. Okay, so let's see what is known so far about this problem. The main result that is known is quite old, like for 15 years old. And it tells us that if you consider a logarithmic annealing schedule, so it grows very, very slowly to plus infinity, then you can guarantee that you'll indeed converge to some optimal transport plans. So here I wrote convergence. I mean, you are not certain to have a unique optimal transport plan in general. So this is convergence up to subsequences to a optimal transport plan. So this is a result by Sharifai and co-author. And this is, if you're familiar with the simulated annealing literature, for instance, for Langevin algorithm or other algorithm with some notion of temperature, this is the standard rate that you get. But it's well known that this is impractically slow. No one wants to use in practice a logarithmic schedule. And why here do we have this logarithmic schedule? It's because the proof relies on this contraction rate that you have in the Hilbert metric, with this very bad dependency in beta. And because this constant deteriorates so quickly in beta, you cannot hope to use this kind of contraction ratio and change the temperature very quickly. So here we can think that perhaps by using the results we have seen in the previous, the first part, we could improve this analysis under the assumption, the continuous distribution assumption in a geometric setting. We could indeed improve this logarithmic rate to some polynomial rate, because this logarithm comes from the exponential here. And if you replace this by some polynomials, you can change that proof and get some polynomial. However, what we will do in this second part is very different. We will not at all need all the assumptions that we made in the previous part in the first part about the geometry of the problem. And we'll get much more insights, in fact, about the behavior of annealed Sinkhorn. So I will just mention in passing two other works that have studied this problem. So there's a work by Schmitzer and co-authors, which studies exponential schedules. So the ones which are used in practice, but he failed, he could not reach to a proof of convergence to the whole scheme. And we'll see that it's normal that he couldn't, because in fact, it's impossible in general. I mean, it's always impossible to prove that exponential schedule converge to optimal transport solutions, as we will see. And then there's a recent work by Balou and Berthet, where they study some other problems, but as a part of their study, they have a result of convergence for annealed Sinkhorn for the average iterate and the polynomial schedule square root of t. So here, the convergence is on the average iterate, and it's not clear for the proof how we could change the result to get some convergence, some results on the last iterate. Okay. So Sinkhorn, we are interested in the last iterate, and so far there is no results besides this logarithmic schedule. And this is practitioners in computational optimal transport have mentioned this as an important open problem to be studied. So this is what we will study now in the second part of this talk. Okay, so the first result that I want to present is a characterization of all annealing schedules that will give convergence to optimal transport plans asymptotically. So what we will assume is that beta is positive. So this is a very natural assumption. You want it to be non-decreasing. That's also very natural. You want it to diverge to plus infinity. And here, the only restriction I will make is that it is concave, which means that the annealing slows down, like the difference sequence alpha t, which is the difference between two temperature, between two iterates, is a non-increasing sequence. Okay, so it's like you want a concave beta to be a concave function of t. So then you will have a limit for beta and a limit for alpha, which I call alpha beta infinity and alpha infinity. And what you can say is that any accumulation point of PT, so the iterates of annealed Sinkhorn, will be a minimizer of this problem, where you have these limits of alpha infinity, of alpha t and beta t. So here this is the difference sequence, and here this is the annealing sequence. So if our goal is to solve optimal transport, you want so here you have two effects. You have the entropic regularization effect, which is still there unless beta diverges to plus infinity. So the first thing you want is beta to diverge to plus infinity, which is not very surprising. But the slightly more surprising one is this other relaxation effect. It's a relaxation because now what you're solving is a optimal transport problem where only one of the marginal is fixed, equal to nu, and the other marginal is only penalized in this variational problem. So you want to penalize the Kullback-Leibler divergence between the first marginal of pi and mu. And the strength of the penalization is 1 over alpha. So you want the strength to diverge to plus infinity if you want to solve the optimal transport problem, so to have this to become a constraint. And so what you want is alpha t to converge to 0. Okay, so this is exactly the characterization of all annealing schedules that will lead to convergence to optimal transport plans up to subsequences. Okay, so here again, convergence is up to subsequence. So I will give a quick idea of the proof, perhaps to explain why we get this relaxation effect due to annealing the Sinkhorn algorithm. So as I mentioned earlier, any plan of the form diagonal A, K, diagonal B is an optimal transport, a solution of entropic optimal transport between its marginal for the temperature corresponding to the kernel you have. So at each iteration, you know that your iterate is optimal for some entropic optimal transport problem with the temperature, with the current temperature, and with the current marginals. So here, since I'm looking at the iterates after having matched the second marginal is exactly new, but the first marginal is something else. So that's pi t1. So you need two things if you want to eventually solve optimal transport. You want beta to diverge to plus infinity, and you want the first marginal to converge to 1. And essentially, these two goals will somehow conflict each other to find the good annealing schedule. So do we have convergence of the first marginal to mu? The answer is not always. It depends on how fast beta d converge to plus infinity. And how can we understand if this is the case? So that's the key, I would say, trick behind the proof, is to interpret this annealed Sinkhorn algorithm as an online mirror descent algorithm on this constraint set, okay, for the Kullback-Leibler geometry. So here you constrain only one of the marginals, and you have a sequence of objectives, which are these functions of pi. So you have a bit of transport cost multiplied by alpha, and a bit of Kullback-Leibler divergence between pi1 and mu. And so what you want is alpha to go to 0. Otherwise, you will never actually minimize the Kullback-Leibler divergence between pi1 and mu to 0. Okay, there will be a conflict here. So since I'm a bit late, I will not get more into detail about the proof techniques. I had a slide about what is online mirror descent and what kind of guarantees we get. But all this is in the paper. What I want to tell now, I mean, unless, of course, you can interrupt me and ask questions, is can we know more and understand which is the optimal annealing schedule? So unfortunately, the optimization guarantees that we get via these proof techniques, they do not give rates which are tight. So if you compare with what you observe in practice, you see some slight mismatch in the exponents of convergence. So we will not use these optimization guarantees to understand which is the best annealing schedule. However, what we will use, sorry, this is the next slide, is a proxy object, which will be used as a proxy for the optimization path. And I will call it the regularization path. This is the set of solutions of this penalized entropic optimal transport, relaxed entropic optimal transport problems. So you see, I just took the problem that is solved asymptotically, but I replaced the limit of alpha and beta by their current values. Okay, so this is not an object which is exactly related to the iterates of Sinkhorn's of annealed Sinkhorn, but we will use this as a proxy to understand how the algorithm behaves. And here I plot also in practice the difference between this regularization path and the optimization path. And in fact, they converge to each other much more quickly than the whole path converge to the solution. So this, in practice, you can observe that this is indeed a very good proxy. And when you look at this object, you see that its suboptimality for the optimal transport problem decomposes in two terms. There is an error term due to the entropic penalty, like the entropic the regularization, which is of order 1/beta. And there is a relaxation error, which is of order alpha t. So this one is due to the fact that we do not match exactly the first marginal. And this one is due to the fact that we still have some entropic regularization unless beta goes to plus infinity. So here, the way that I'm measuring suboptimality for the optimal transport cost is an interesting story. I mean, I really like it. It's an idea due to Altuler and co-authors, where instead of, I mean, to measure how we are the suboptimality at iteration t for the iterates of Sinkhorn algorithm and suboptimality in terms of the optimal transport problem, you need to project or to bring back your iterate to this set of transport plans. Otherwise, you would compare a non-feasible iterate to a problem over a certain constraint set. So they have a very nice trick to do a very fair evaluation of the suboptimality. I will not really go into the details, but this is a good measure of suboptimality, and it is upper bounded by these two terms. And for instance, if you take polynomial annealing schedules of the form t to the kappa, then you get a bound of order t to the minus kappa plus t to the kappa minus 1, which is optimal when kappa equals 1/2, so the square root of t annealing schedule. Okay? So this is what you get when you optimize the upper bound. And in the next slide, we can wonder whether this is indeed what we get in practice. So is this annealing schedule the optimal one? The truth, I mean, that's the truth, that's the case. For any kind of problems, you don't need to have a particular structure or anything. You will always observe the blue curve here. So here I plot the suboptimality at iteration t equals 200 as a function of the exponent in the annealing schedule. And we see empirically that 0.5 is close to the optimum one. And this does not really depend on the kind of problem that you have. So the empirical prediction, the theoretical prediction we made is confirmed by this experiment. So that's a strong limitation of annealed Sinkhorn. It tells us that you cannot increase the temperature faster than square root of t. And in this slide, so I will go quickly because I'm maybe a bit late on the schedule. That's the last slide, in fact. I know that's not the last slide, so I will go a bit quickly. In this slide, we wonder whether it's possible to change the algorithm so as to use faster annealing schedules. And to do this, one idea is to try to remove one of the error terms, at least to replace one of these error terms in 1/beta or in alpha by a higher order error term. And this is indeed possible. So here we use a trick where we modify the marginal mu in such a way, using the dual solution of the optimal transport problems in such a way that when you solve the relaxed problem of the regularization path, you will get a smaller error in terms of alpha. So you can keep the first order error term. So without this modification of the first marginal, you will get a big theta of alpha t here. And by modifying the first marginal, you can get to little o of alpha t. And when you plug these kind of estimates into the annealed Sinkhorn algorithm, this gives you a slightly modified algorithm, which I wrote here. So it has exactly the same computational complexity. You just have this red factor here, which is which you insert in the algorithm, which is predicted by the theory. And once you insert it, you observe that you can use much faster annealing schedules. And in fact, if instead of the little o here, what we get is a big O of alpha square, this would suggest that the optimal annealing schedule, by optimizing the trade-off, you will get t to the 2/3. And in practice, you in fact see that you can use essentially an exponent of annealing schedule of order 0.66, so 2/3. So with this modification of annealed Sinkhorn, you can accelerate the annealing, and again, you cannot really do better. So that's a trick. Here, I do not have at all a convergence proof for this algorithm because it's just an intuition that we gain from some from the proxy of the optimization path of how to modify the algorithm to make it work better. It works in practice, but it's very difficult. I mean, we don't have an analysis at all of the convergence of this modified algorithm. And now I will conclude on some final numerical experiment where we will compare Sinkhorn versus annealed Sinkhorn and debiased annealed Sinkhorns. So here we only see the behavior of Sinkhorn algorithm to solve optimal transport. So I plot the suboptimality as a function of the iteration. And the color here depends on the temperature that you have chosen for Sinkhorn's algorithm. So standard Sinkhorn has a fixed temperature. So it will converge quickly, but to some plateau, because in the end, beta is fixed, and we are not solving the optimal transport problem. So there is some irreducible error, which is the final plateau that we get here. So by trying a lot of values of beta, you get many curves. And you see that if, in hindsight, you have a certain computational budget and you wanted to reach a certain accuracy on the optimal transport problem, you could know which was the best choice of regularization beta to be used. But of course, you cannot know that a priori. So to find, I mean, here you need to run Sinkhorn algorithm many times in order to observe this curve. And you cannot directly solve the problem on the speed accuracy Pareto frontier, which is the minimum of all these curves here. Now, when you do annealed Sinkhorn, with the optimal annealing schedule, which is square root of t, you get a convergence in 1 over square root t. So here, this is not a convergence rate that we have proved in practice. But this is the convergence rate that we have proved for the proxy regularization path. Okay, and that's the one we observe in practice also for annealed Sinkhorn. And we see that it's slightly worse than the Pareto frontier that we get for Sinkhorn. So it's advantageous because here you only need to run the algorithm once to get this whole speed accuracy trade-offs, but you're far away from what Sinkhorn can do if you had known the best regularization beta in hindsight. And now when you use the annealed Sinkhorn with debiasing, what you get is this curve. So you see that you are very close to the Pareto frontier of Sinkhorn. Sometimes you even beat it. So here, this is a transport problem in a geometric setting. Sometimes you are slightly worse than the Pareto frontier, but in all the experiments I've done, the debiased annealed Sinkhorn was very close to the Pareto frontier of Sinkhorn. And here you get this only with one run of the algorithm, all the optimal speed accuracy trade-offs. Okay, so that's the end of this talk. Here I've listed the two references on which the two parts were based on, and some open questions that remain around these questions. So thank you for your attention, and I can take questions.
Thank you very much, Lenaïc, for this great talk. There were some questions already during the talk, but still, are there questions left? Then please post them now. Yeah, so I can start with one short one. So I mean, it is basically what you already wrote here. I mean, what is left now in this final slide? Do you think that this debias idea will get you to the Pareto frontier, or is there something left to do there?
So
this modified annealing schedule, it almost reached the Pareto frontier. Do you think that it does, or is there some more work to be done there?
Well, so at least in this experiment, it beats the Pareto frontier, so that's even better. Sometimes it's slightly behind, but the slope that I could observe in all my experiments, so I've tried experiments with random point clouds in high dimension or some experiments in low dimension with some geometric setting, like continuous density, discretization of continuous problems. And I've always seen the similar slope in -2/3. However, I cannot claim much more because I think the analysis of the debased Sinkhorn algorithm would be very tricky. I already do not have a proof of this rate of convergence for Sinkhorn in -1/2. Sorry, in t to the -1/2. What is proved in the paper is there is a proof of convergence in t to the -2/3. So that's the one you get from this online mirror descent interpretation. But as you see here, it's not tight. So I don't know if it's what can be reached theoretically, but of course that would be a very interesting question to understand what is this Pareto frontier rate and whether there are some algorithms that actually we can prove achieve the same rate. Yes.
Thank you. There does not seem to be more question. So then
Lenaïc.
There is.
Yeah. Lenaïc, thanks for the talk. I learned a lot. Very possibly stupid question, but on the plot where you were showing, I think like at iteration 200, here's what you get for these different schemes. I was slightly bothered by the fact that on the second one, it doesn't seem like the minimum's at 2/3. It looks more like 3/4. That just an artifact of the experiment, or?
Yes, so here I believe this is an artifact of the fact that I'm looking at a non-asymptotic way because it's 200 iterations. Okay, so 2/3 will be here, and what we get is here. To be honest, I think there are many things that enter into account that would perturb this prediction of 2/3, which is again not fully theoretically backed up because it's only if we assume that instead of this little o, we have a big O of alpha. So it depends on the stability of the optimal dual solutions. So it depends really on the problem, on many things. I think there are some settings where if the optimal transport problem that you try to solve is really stable in the sense that it has a unique solution, I think we would get something very close to the 2/3. But here there is some, I would say, noise or some imprecision due to the fact that I might be solving a problem which is not that stable, and so the debiasing does not work as much as it could asymptotically. So there,
yeah.
I'm already happy, I would say, that it's not close, not far away from the 2/3. But yeah, that's a good remark.
And the Pareto, the other plot you showed, I thought was quite nice and convincing, at least as far as it goes.
Yeah, I agree. Thank you. Yeah, sorry, I went a bit over time.
No problem at all.
Yeah.
But now it generally does not seem to be any more questions. So I thank you again, Lenaïc, and see you at the next seminar.
Thank you very much. Bye-bye.